Earlier lectures on heat transfer, from 28 lecture to 32, I have introduced to you to the concepts of heat transfer and application to heat exchanger, heat flow through furnaces and so on, radiation principle also. Few problems I have also solved in those lectures to appreciate the fundamentals. Today I thought that let me explain more the theoretical concept by solving some more problems. So, I have selected one of the important area to illustrate the theoretical concept and its application is the heat exchanger. Now, in fact, it is known that all fuel fired furnaces, the thermal energy of the fuel is available in the form of products of combustion, as we have seen in the lectures on combustion. The products of combustion transfer their energy to the furnace, heat the product to the desired temperature, and depending on the furnace temperature or product temperature, the products of combustion exit the furnace. From energy security point of view, also from environment sustainability point of view, as I have illustrated in my introductory lecture, that it is necessary to recover the heat of products of combustion, particularly when the VOC are exhausted at a high temperature, for example 700 or above that degree Celsius. However, heat recovery at lower temperature is also important. So, it is from that consideration the high temperature industrial furnaces, those operating on fuel fired one, or where the thermal energy is derived by combustion of fossil fuel, nowadays it has become very important that how to economize the consumption of natural energy resources, so that for the future the energy resources can be conserved. And it is in this relationship the government has initiated several steps like carbon credit, carbon offset, clean development mechanism and so on, to encourage the entrepreneurs working on high temperature furnaces to take measures to economize the fuel consumption. Some of the idea of clean development mechanism I have already introduced when I was taking the lecture on carbonization, that is the coking coal. Now, heat exchanger is one of the important concept to recover the heat of products of combustion. Essentially, the fundamentals of heat exchanger I have introduced in the lecture 31, 32. You can collect those fundamentals. The one of the important objective of heat exchanger is to exchange the heat between the hot fluid and the cold fluid. That is the whole reason. It is necessary for this that you have to optimize the dimensions of heat exchanger. By the dimensions I mean the length of the heat exchanger for a given cross sectional area of the heat exchanger. Length is important because that will decide the residence time, whereas the cross sectional area will decide the velocity of the fluid with which the fluid is moving in the heat exchanger. So, both will decide the residence time of the fluid, of the hot fluid and as well as cold fluid, and depending on the optimization of residence time, the heat recovery is possible. So, those fundamentals I have illustrated. Now, one can think of for recovery of heat from flue gases two possible ways. In one way, the hot fluid is flowing co-current to the air That is, for example, you want to preheat the air or you want to preheat the water or whatever fluid you want to have. One way is that a co-current and another is the counter current. The situation can be represented by this. For example, in a co-current flow, suppose this is an heat exchanger, or we can call it as a recuperator. There, this is the hot fluid is flowing, say at temperature TH1, and it is discharged at temperature TH2, and here in the coaxial tube, the cold fluid is entering. This is at temperature Tc1 and at temperature Tc2, and this is the length of the heat exchanger. That means here the hot fluid is flowing this way, whereas cold fluid is flowing this way. Ultimately, it is out. So, this is a co-current. Now, in another, we can also think of a counter current. In a counter current, it goes like this, though I have illustrated, but for the sake of solution of the problem, I will just repeating important concepts. So, this is the one. So, here you have hot gas which is at temperature TH1, this is at TH2, here is the cold fluid, it could be air or it could be water, because we want to exchange. This is the Tc1 and this is the here Tc2. That is, this is the direction of flow of hot gas and this is the direction of flow of cold air. And there I have also said that in utilizing the expression for heat exchange, it is important that the temperatures are chosen, they are the inlet and exit temperatures of the heat exchanger. While teaching this course for several times at IIT Kanpur, invariably I observed that most of the students, they do error in substituting the temperatures. They think that the temperatures involved in the expression, they correspond to the fluid temperature. No. Remember, strictly no. The temperatures involving in the expressions are the temperatures at the inlet of the exchanger and that of the outlet of the exchanger. So, if we now plot, for example, here, if we take on this axis as T, temperature, here it is a 0 length, the entry, and here is the length of the exchanger. So, I just complete it. Same thing I do it also here. This is the length of the exchanger and here I take the temperature. Now, in the co-current, this my point is TH1. This is my TH1. So, this 0 that let us call this is inlet of the heat exchanger. This is the inlet and this is the outlet, or you can call entry and exit temperature. So, same way for the counter current one, this is the inlet and that is the outlet. Mind you, these are the inlet and outlet of exchangers. So, in this way, this one is a counter current. This is the counter current. So, if you want to show how the temperatures are varying at the inlet and exit, and those temperatures are to be substituted, mind you, because several students do this type of mistake invariably. That is what I have observed. So, I thought I will explain to you. So, how the temperature of hot gas, it varies, say entry, then it goes somewhere here and this is the temperature TH2. Now, similarly, for air, this is the one Tc1, and the air temperature, it increases and goes to Tc2. Now, also remember that the temperature of hot air can never exceed at any point the temperature of the flue gas. So, this, for example, the variation of temperature for flue gas, and this one, for example, the variation of temperature of air. Now, this is also important to note that the students also do the mistake while showing the variation of temperature. They sometimes cross the air temperature at some length of the heat exchanger to the temperature of the flue gas, which is impossible. Air cannot be heated at any length of the heat exchanger to the temperature above that of the flue gas. Remember, and that mistake should not be done. So, that is how this is for the co-current, and in the co-current you notice that the inlet temperatures are TH1 and TC1, whereas outlet temperatures are TH2 and TC2. These are the inlet temperatures and these are the outlet temperatures. Now, let us see how for a counter current this looks. So, in a counter current, say we have here, no doubt, this is the TH1 and this is the variation of flue gas, TH2, this is that of the flue gas. Now, here the TC1 is somewhere here, remember, this is the TC1 and the temperature increases and there you have, here you have TC2. So, the inlet temperatures of a counter current heat exchanger, that is TH1 and TC2, whereas that of the outlet is TH2 and TC1. So, that is the main difference while applying the equations which were developed for heat exchange in counter current or co-current flow of the fluid. The temperatures, again and again I will say that the temperatures are inlet and exit of the heat exchanger. That is the important thing. And as I said that the difference in temperature between flue gas and air, or between whether it is co-current or counter current, is because of the irreversibility that is introduced by thermal resistance of the wall of the heat exchanger and because of the flowing fluid. So, those things are to be optimized in order to obtain the maximum heat transferred from flue gas to the heating fluid. So, that is the important thing, please remember. Now, having said this thing, as also I have said that in order to define the efficiency of heat exchangers, I have introduced these formulas. Let me write once again. So, efficiency of heat exchanger, refer details in lecture 31, their details are given. I am just giving it the formula for use in the solution of the problem. There we have defined overall thermal efficiency, and this we have defined that sensible heat in air, upon sensible heat in flue gas. You recall that sensible heat in flue gas multiply by 100. We had also defined the so called efficiency limit, and the concept of efficiency limit is that an exchanger of given length and a given cross sectional area can recover the maximum amount of heat, and this efficiency limit we have defined as, say, sensible heat in air sensible heat in air at hot flue gas temperature, because this is the maximum that you can derive it, upon sensible heat in flue gas. And this efficiency limit is a term where one can note that what is the maximum amount of heat that can be recovered from the flue gas. Then we also define the relative efficiency. We also defined relative efficiency, and this relative efficiency, in fact, it compares the behavior of different heat exchangers in different locations, because this relative efficiency, it tells you how much amount of air or how much amount of heat is being extracted by a particular exchanger, and that is defined as, you recall, that is sensible heat in air, sensible heat in preheated air upon sensible heat in air at hot flue gas temperature. Hot flue gas temperature in 200. So, really if you want to compare how the heat exchangers are working in two locations, then you just calculate the relative efficiency, and one which has a higher efficiency that works better as compared to the another one. Now, also to note that heat exchange, it depends upon it depends upon, say, type of flow, that is whether it is co-current or counter current. But in our derivation which I have derived for the heat flow through the exchanger, this co-current or counter current does not enter into our derivation. Suggests that whether co-current or counter current, it does not affect the derivation part of it, but the co-current or counter current affects the inlet and exit temperatures of the heat exchanger. That point is to be noted. Heat exchange also depends upon the heat exchange area. Heat exchange area, because you require certain minimum area for transfer of heat. Then length of heat exchanger, and residence time of cold fluid and hot fluid, and definitely the residence time is being determined when the cross sectional area of the exchanger is fixed and the flow rate will determine. So, what I mean, the problem now can be formulated considering these 4 points under consideration. So, let me take one problem to illustrate this thing. Let us take it for example, hot exhaust gases at 1250 kilogram per hour are flowing at 480 degrees Celsius through heat exchanger and cooled to 180 degrees Celsius by water flowing initially at 20 degrees Celsius and at 1550 kilogram per hour. The overall heat transfer coefficient, is 125 kilocalorie per hour meter square degree Celsius. Calculate surface area. Calculate surface area required under two conditions. One condition, when the heat exchanger is co-current type, that is for co-current heat exchanger, and when heat exchanger is of counter current type. So this is what we have to find out, the area which is required. So as such, in order to proceed this problem, first of all we have to know what are the inlet and exit temperatures of the heat exchangers. So for that, we again schematically sketch. Say this is the one. Here hot flue gas is at 480 degrees Celsius, coming out at 180 degrees Celsius. Here water is flowing at 20 degrees Celsius. This temperature is not known. Exit temperature is not known. This is definitely a sort of co-current here. Similarly, for counter current, we can also draw it. So counter current, this is entering at 480 degrees Celsius, going out at 180 degrees Celsius. Water is entering at 20 degrees Celsius. You have to find out the exit temperature. These are not known. So if you want to represent over the length of the heat exchanger, just now I had explained. So it is 0. This is the length L, 0 and length L. This is for the counter current. For the counter current, now the hot flue gas, its temperature will vary. For example, from 480 degrees Celsius will go to 180 degrees Celsius, and here it starts from, say, this water starts from 20 degrees Celsius, and we have to find out what is this temperature. In case of here, the hot flue gas, it goes this way. This is 480 degrees Celsius. This is 180 degrees Celsius. Whereas this water is here is 20 degrees Celsius, and we have to find out this particular temperature. So that is what, to start such type of problem, this representation is very good. If you can represent it, then you know what to be done. Now first of all, we have to find out the outlet temperature of water, and for outlet temperature of water you can find out by doing the heat balance. So by performing heat balance, what does it mean? That means heat given up by the flue gas, that will be equal to heat taken up by the water, on the assumption that no heat losses are there. On the assumption no heat loss are there, then heat given up by the flue gas, that will be equal to heat taken by the water. So we can write down as a qualitative statement, the heat given by flue gas, that will be equal to heat taken by water what I have to do? I have to now simply substitute heat given by flue gas. So, if I substitute say by flue gas, the flow rate is for example 1250. Let me give you one more value that we will be requiring. So, let us take Cp of flue gas, let us take equal to 0.27 and Cp water let us take equal to 1 in SI units. So, 1250 into 0.27 heat taken by water. So, water is flowing at the rate of 1550 into 1 into T2 is the temperature of exit, water at the exit, minus say 20. So, our basis of calculation is say 20 degrees Celsius. So, if we solve this equation, we will be getting say for example T2 that will be equal to 85 degrees Celsius. So, this temperature now we have determined equal to 85 degrees Celsius. This is here 85 degrees Celsius. Now, we can apply our equation, that is Q U A0 TH1 minus TC1 minus TH2 minus TC2 upon ln TH1 minus TC1 upon TH2 minus TC2. This is for the both co-current or counter current. All that we have to substitute the proper value of the temperatures. So, if we do that, now the value of Q we know, that is 1250 into 0.27 into 300. U is given to us 125. A0 we have to find out. Now, for co-current, I am writing down for co-current 480 minus 20 minus 180 minus 85 upon ln 460 upon 95. So, if I solve, I will be getting A0 that is equal to 3.51 meter square, that is for the co-current. Now, the value which I have substituted, from that value itself we can know that these are for the co-current, because that you can see what inlet and exit value I have substituted in the equation. So, it is for the co-current. Now, similarly, I substitute for counter current. Similarly, I substitute for counter current. So, for counter current, I will leave this exercise to you. You substitute the proper temperatures and you will be getting A0 that is equal to 3.11 meter square. So, please substitute the correct value of the inlet and exit temperature of the heat exchanger. I am leaving this exercise, you should do it, and to get the answer, that is 3.11 meter square. Now, what this result means? Though in the derivation of the heat transfer in heat exchanger, we have said that the derivation, it does not take into account the co-current or counter current in terms of the temperature. But now, we can see that the co-current or counter current, they will be good or bad depending upon the how much heat exchange area is required. So, you are seeing a counter current exchanger, it requires less heat exchange area as compared to co-current heat exchanger, and it is well known the heat transfer by the flowing fluid will always be better when there is a counter current as compared to when there is a co-current. So, that is what the illustration through this particular problem. I will take one more problem because in industry for high temperature heat recovery sometimes regenerators are used. Now, the recuperators are used when the temperature of the hot flue gas is lower, because they are of the metallic construction and hence lower, they are suitable for lower hot flue gas temperatures. If you want to go for higher flue gas temperatures, then the regenerators are used. And as I have said that the regenerators, their construction is that of the brick checker work. In the heating cycle, the flue gas flows and heat is recovered in the brick. In the cooling cycle, air passes and heat is transferred from the brick to the air. Keeping this analogy, we have said that the thermal resistance are comparable to that of the recuperator, and we have said that the similar expression will be applicable as we have derived for considering the heat exchanger, say in case of recuperator. So, let me illustrate by taking an example of a regenerator. So, a regenerator receives hot flue gases at 1400 degrees Celsius and cold air at 25 degrees Celsius. The flue gases leave at 750 degrees Celsius and air is preheated to 1100 degrees Celsius. An estimated 15% of the heat given up by flue gases is heat loss to the regenerator surroundings. That means 85% of heat is recovered in preheated air. You may assume, assume Cp that is equal to 0.52 watt per meter degree Celsius for flue gas and 0.43 watt per meter degree Celsius for air, independent of temperature. Now, estimate first part A. Estimate overall thermal efficiency, efficiency limit, efficiency limit and relative efficiency of this heat exchange operations, of this heat exchange operation. So, this is an illustration of calculation of overall thermal efficiency, efficiency limit and relative efficiency. Then in the next part, we will see how to calculate the other parameters. So, this is the problem. I am presenting a solution to this problem, but my request to the listeners of this video lecture, or my request or my appeal to this listener of the video lecture, is that please solve this problem yourself before seeing the solution of this particular problem. Because if you can solve this problem, many things will be clear. So, I again appeal to the listeners of this video lecture to please solve this problem without going into the solution. So, let me solve this particular problem. Now, here flow rates of air or flue gas, they are not given. So, as such, seeing the problem, the calculations of overall thermal efficiency, relative efficiency limit and efficiency limit, it is not possible to calculate, because those values are required when you want to calculate the efficiency, sensible heat and so on and so forth. So, for that, if you do heat balance, the clue to solve this problem is the heat balance. If you do the heat balance, then you can get some of the hidden variables like that. Say M air, that is heat recovered by air, M air, Cp air 1100 minus 25 that is equal to M flue gas, Cp flue gas can recover 1400 minus 750. Now, heat given by the flue gas, that will be equal to heat taken by the air. But now, here it is given that only 85% of the heat given by the flue gas can be recovered in air. So, we have to multiply this by 0.85. So, this is the starting for solution of this particular problem. So, now from here we can get M air, Cp air divide by M flue gas, Cp flue gas, that will be equal to 0.85 into 650 divided by 1075, and that will be equal to 0.514. So, we got this ratio now. Now, for example, we can calculate overall thermal efficiency. We calculate overall thermal efficiency and you know, whenever you calculate any problem related to heat transfer or related to heat balance, a basis of calculation is to be specified. So, here as such, the basis of calculation is 25 degrees Celsius. So, in the definition of overall thermal efficiency, sensible heat in preheated air upon sensible heat in flue gas, you know this definition. So, I am directly substituting, that is M air, Cp air into 1100 minus 25, that will be equal to Mf Cpf 1400 minus 25, because Here now the sensible heat in flue gas, and that sensible heat will correspond to your basis of temperature, remember, multiply by 100. So you see now M air, Cp air, MF Cpf, you do not require their absolute values of M air or MF air or MF flue gas. Directly you can substitute the ratio into 100 and the answer would be 40.18%. Similarly, one can calculate efficiency limit. I leave it to you, and the efficiency limit will come out to be equal to 51.4%. Please solve yourself. Formula, everything is given. And then next, to calculate relative efficiency, is simply overall thermal efficiency upon the efficiency limit, and the answer will be 79.4%. So this is the answer for the problem which is being asked. Now I am extending this problem to little further. What I am telling now, part B, suppose now both, that is depth of regenerator and heat exchange area were increased to 2.5 times while keeping constant the overall heat transfer coefficient, that is U in watt per meter square Kelvin, the quantities and entering temperatures of both fluids, that is air and flue, of both fluids will be kept same as that of earlier. Now estimate for this enlarged generator, regenerator, A, air preheat temperature, B, overall thermal efficiency, and C, relative thermal efficiency. So now you have to solve this particular problem. Now note that in this problem nothing is said whether the flow is counter current or co-current. You have to apply your mind to see first of all how the fluid is flowing. If you do not apply your mind how the fluid is flowing, you are liable to do mistakes to the extent of 99.99%. So first of all you have to know how the fluid is flowing, because the problem does not mention whether it is co-current or counter current. You have to apply your brain here. So first of all you have to decide What are the entry and exit temperatures of the heat exchanger? In the earlier problem, those temperatures were defined. Here they are not defined. So, now let us draw. This is, for example, a regenerator. This is the height of the regenerator, right. Now, what I am doing here, hot flue gas is flowing at 1400 degrees Celsius. Hot flue gas is flowing here at 1400 degrees Celsius, and in the earlier problem it was said that it is exiting at 750 degrees Celsius. Now, it is not possible to heat air more than the flue gas temperature. So, correspondingly, this air has to be entered from here at 25 degrees Celsius and air exit that was given to us 1100 degrees Celsius. We cannot show that air entry from top at 25 degrees Celsius and air exit as 1100 degrees Celsius, because it is not possible. Air temperature cannot go more than the flue gas temperature at any height or length of the heat exchanger. That is the clue to solve this particular problem. That you should understand. You cannot show, once again I repeat, you cannot show that air is entering from top at 25 degrees Celsius and exiting at 1100 degrees Celsius, which is impossible, because air cannot be heated up more than the flue gas temperature. Once you got this idea, then the problem is very simple now. So, now in the problem which I just said, we will show again. We are given with the inlet and exit temperature. So, again here it enters at 1400 degrees Celsius. This exit temperature is not known. So, let us take it. This exit temperature, for example, TH2, which is not known to us. Then this is the inlet temperature. Let us take, this is known to us 25 degrees Celsius, and this temperature TC2 is also not known to us. Now, once you have developed this field of representation of this problem in this particular diagram, then of course the solution of the problem is very easy. So, now what we can do now, if we take, because this B problem which I have given is an extension of A, which is said that now you are increasing the height of the regenerator to 2.5 times. That is what you are doing it. So, we have to calculate first of all, the heat transfer case for the first one. So, for the first one, you say the equation which was there, say ln TH2 minus TC2 upon TH1 minus TC1, that is equal to U0 1 upon MH CPH plus 1 upon MC into CPC into 2 pi R0 into L. So, what we have to do now? We have to substitute the values here, and because this we know it, so this is ln 750 minus 25 upon 1400 minus 1100, that is equal to U0 into 1 upon MH CPH plus 1 upon MC CPC into 2 pi R0 L. So, now we can get, so this value, that is equal to 0.882, that is equal to this particular thing. Now, the problem says that we are increasing height 2.5 times, MH, CPH, they all remain the same. So, now our second equation will be ln Th2 minus 25 divide by 1400 minus Tc1, that is equal to 2.5 into 0.882. So, that is what you will proceed to solve this particular problem. So, if you solve it, then I will be getting Th2 minus 25, that is equal to 12,698 minus 9.07 Tc1, that is my equation number 1. Now, second equation I will be getting by heat balance, that is Ma Cpa Tc1 minus 25, that is equal to 0.85 Mf Cpf 1400 minus Th2. So, I substitute all the values, then I will get the second equation, and second equation is 0.605 Tc1 minus 15.11, that is equal to 1400 minus Th2. This is my equation 2. I can solve both equations simultaneously. So, I will be getting here Tc1, that is equal to 1335.8 degrees Celsius, and Th2, that will be equal to 557 degrees Celsius. Please solve yourself. Then now once I know this thing, then I can calculate the overall thermal efficiency. Overall thermal efficiency, that will be equal to 49%, and relative efficiency will be equal to 49 upon 51.4 into 100, and this you can solve it, that will come around 50 or something percent. So, that is how the solution of the problem. Now, I will request you to solve the same problem. If suppose the height of the regenerator is doubled, rest everything remain the same, then try to see what is the air preheat temperature and overall thermal efficiency. So, my whole objective is to illustrate the how to calculate and how to apply these equations to solve the heat exchanger related problems.